Galaxies make up a huge chunk of what we can detect in the universe. They come in all sorts of shapes and sizes, and some can get really big, like IC1101, which is 20 times larger than our own Milky Way galaxy. That's pretty damn massive. But what if you want to look towards the other extreme? How small can a galaxy get for it to still be considered as a galaxy? Surprisingly, this question is much harder to answer than it may first seem. Hello everyone, and welcome back to the C-Squared channel. So that we can delve into today's topic, we need to make it clear to know what a galaxy actually is. For something that has been observed for a really long time and seen all over the universe, there actually isn't a formal definition of a galaxy. There have been many proposed definitions to draw a line between what a galaxy is and isn't, and this links quite nicely to the question of how small a galaxy can get before it is no longer classified as one, simply because the line here is not well defined at all. If you want to know a little more about galaxies themselves, I made a short video earlier in the month talking about this topic in a quick minute, so be sure to check that video out for just a few more details. Out of all the proposed definitions for a galaxy, one in particular that struck out to me comes from a research paper called Galaxy Defined by Dr. Beth Wellman and Dr. Jay Strader. They define a galaxy as a gravitationally bound collection of stars whose properties cannot be explained by a combination of baryons and Newton's laws of gravity. Now that's quite a handful, so let's break that down just a little bit. From this definition, baryons refer to particles like protons and neutrons that make up, atoms. These are known as baryonic or ordinary matter, and Newton's laws of gravity essentially fall into your standard classical mechanics principles that would govern stellar motion in this situation. What this definition means, therefore, is that if you try to describe these stellar systems with only Newtonian mechanics and with baryonic matter, you would get an incomplete understanding of the system, which, under this definition, is a galaxy. If Newtonian mechanics and baryonic matter are enough to fully explain observed properties of a system, then it is not a galaxy. A very good example of a case that satisfies this definition is if you take a look at a spiral galaxy and you measure the rotational velocities at any radius from the center. You would find that the observed rotations are way off from the calculated theoretical rotations. This huge discrepancy is due to non-baryonic, so-called dark matter, which simply classifies spirals as galaxies under this definition. This dark matter exhibits interesting gravitational influences on galaxies, and in the case of spirals, explains why the rotations on the edges are so much greater than what should theoretically be possible. Both Willman and Strader ran tests for many types of star systems and found some rather interesting results that seem to be in line with actual observations using this definition. I put a link to the paper in the description below, so I would strongly recommend taking a read if you're interested in knowing more about this topic. For the rest of the video, I'll be using this one definition of a galaxy for consistency. Now, having some definition of a galaxy is important because we can actually begin answering our initial question. Unfortunately though, the answer is still quite difficult to come to because even though yes, we have something to work with now, that's perfect, the line is still blurred between a tiny galaxy and a large star cluster. So we need to make a few more distinctions before we move on. There are many different ways to define small in the context of galactic astronomy. There's small as in how many stars make up a galaxy, and there's small as in the physical size, so how compact and dense stars can get in a volume of space. For this video, I want to focus solely on the stellar content of galaxies. Now, even though we're just going to be talking about star count, there are actually quite a lot of interesting things that can be talked about here. The smallest observed galaxies, looking at star count only, appear to have extremely low populations of stars on the visible end of things, as you would expect. These are typically the Dwarf spheroidal galaxies, or DSPH classification, and many of them exist orbiting around our own galaxy, the Milky Way. The challenge for astronomers in detecting these is that they are extremely difficult to even find them to begin with. Most of the dwarf spheroidal galaxies we've seen have very few stars compared to the much larger galaxies we're typically familiar with, which of course makes a lot of sense, because these are tiny in comparison. These galaxies have really low luminosities, and so they appear to be very faint. Although, how low can we go in terms of star counts so that it can still be considered a galaxy? Well, it turns out that we can go very low with these star counts. And by very low, I mean very low. Let's start with the Hercules dwarf galaxy, for example. This is, to nobody's surprise of course, a dwarf spheroidal galaxy located about 140 kiloparsecs away from us and is orbiting the Milky Way. If you were to try and estimate the number of stars in this galaxy, a reasonable value would be a couple 100,000 or so. Already, that is actually quite tiny. Some of the largest star clusters that we know of, which are not galaxies might I add, can have up to tens of millions of stars. So, is this maybe the lower limit of galaxies then? Absolutely not. We found smaller. Leo 4 is another galaxy of the same class, which is located 160 kiloparsecs away, and is also orbiting the Milky Way. Unlike with the Hercules dwarf, however, this galaxy somehow seems to be composed of even less stars, at an estimate of just a few tens of thousands. Okay, so surely that's the lowest though, right? We can't go smaller than just tens of thousands without it no longer being a galaxy at this point, you'd think. Well, you'd be wrong. Amazingly, we can still go further. And this brings us to Segue 1 and Segue 2. Possibly the smallest galaxies that have ever been observed and recorded in history. Now, Segue's 1 status as a galaxy is currently disputed, but we have a safe bet to call Segue 2 a galaxy from observations. We'll just consider Segue 2 to avoid this ambiguity. But even then, Segue 2 only has 1,000 stars in it, which is comparable to that of an open cluster, which is one of the smallest collections of stars you can have in the universe. But why are these still galaxies? Surely things this small doesn't seem to make sense to still call them galaxies, right? In cases of, like, Segue 2, we only have about 1,000 stars, yet this still seems to satisfy the conditions of being a galaxy under the definitions that we made initially. What is going on? Well, remember what we discussed earlier about our definition. It seems like these objects still satisfy this definition because of one crucial detail. We need to consider something called the mass-to-light ratio, which relates the mass of a galaxy, in solar masses, with its luminosity, in solar luminosities. For ordinary galaxies like our own, this ratio is typically anywhere in the range of about 2 to 10. That's kind of a standard value for most galaxies. What is rather intriguing, however, with galaxies like Segue 2, Hercules dwarf, and Leo 4, is that they all have extremely high mass-to-light ratios in comparison to what we know with standard galaxies. Despite the fact that these tiny galaxies have very few stars and really low luminosities. So what does that mean? To have such low luminosities but a really high mass-to-light ratio implies that these galaxies have an extremely high mass content, despite having very few stars in their systems. It's very unlikely that all of these stars would be so massive to match this mass in the galaxy. So this must mean that they are dominated by dark matter to account for all of this missing mass. For example, Leo 4 has a mass-to-light ratio of 150. Even though it only has a few tens of thousands stars, the estimated mass is 1.5 million solar masses, which is insanely huge for this tiny of a star count. And so to explain this missing matter, it's rather safe to say that dark matter is what this galaxy is mostly composed of, which nicely leads us back to that definition of a galaxy we talked about at the very beginning of this video. We can't explain this extreme mass-to-light ratio for a galaxy that has such few stars and low luminosities using only standard baryonic matter that we can deal with. And so we need dark matter to account for this missing mass, and that qualifies this as a galaxy. If you were to measure such things for, say, open and globular clusters, you would find that the mass-to-light ratios look more in line with observations. Hence, they are not galaxies, since it would be enough to describe with standard baryonic matter alone, and you won't need dark matter anywhere in these situations. So to answer our initial question on how small galaxies can get, they can get extremely small in the visible end of things, The lower limit could perhaps be even a single star for all we know. But as long as it is dominated by dark matter, and the mass is still significantly large, then we could still perhaps treat it as a galaxy under the definition designed by Willman and Strader. With observation techniques being more refined in the future, we can expect to find so many more tiny galaxies like Segue 2 in the years to come that will most definitely challenge what we already know about galaxies once again.